The correct answer for this problem is 25.7 kilograms. So for sig figs and for units, this is what you should have ballparked. Not exact answer, but close to it. How many of you were kind of near there? In the 20s? Like 2 or 3 of you. So I'm hoping as I continue with this right now, like all of you will eventually get there, but let's talk about how to handle each part. So you may come up with a different technique, and I like that. Some people showed me in block 2 that they had sort of a different approach to some of the problems that I solved. There are many approaches. I'm just going to show you how I sort of would handle them. So the first thing I would do is I would look at 908 and multiplying that by 0.4536. I recognize that this is basically like 0.5, right? But I'm estimating a little bit over. So when I take this 908 and multiply by 0.5, it's kind of like dividing it by 2, isn't it? Because 0.5 is 1/2. So if I take 908 and divide that by 2, I'm looking at 450 into times 2 is 900, right? And then that 8, divide that by 2, so 454. Do you agree? So I'm about at 454 for my numerator. But again, I'm ensuring here that I recognize that I rounded up here. So really then my answer, if this is my answer and I multiply by 0.5, it really should be a little bit less, right? So sometimes I'll just kind of put a little down arrow or an up arrow to tell myself my real answer should be less than this, or my real answer should be more than this, just in case the answers are close by. All right, then I'm going to divide this by 16. So at that point, right, you could do long division like you're in 4th grade again, but I like to look at numbers that are common to my 4th grade math that I know. Like basic math, 45 divided by 16 is easier to do. So I could do like 16 times 2 is 32, plus 16 is 48, right? So that's kind of close to 48, 45. So I'm going to say, well, that was about 3. I came up with an answer that was about 3. But 48, right, I would really be a little bit less because 45 is less than 48. So here my answer should be less, and I already said that this number should have been lower, so this is probably going to be a little bit less than this. And now I'm going to handle how I did this part. So I had my coefficient, so really I did 45.4 times 10 to the first. Put everything in scientific notation when you're handling your coefficients. And then I had 16 times 10 to the 0. So that's how I did 45 divided by 16. I got roughly 3, but it's going to be less than 3. And then I handle my exponents. So 1, and when you divide exponents, you subtract them, right? When you multiply exponents, you add them. So 1 minus 0 is still 1 times 10 to the first. So my answer is going to be less than 30, essentially. And that's how I got 25.7. If you get an A, B, C, D, and the answers are really close together, like maybe there's a 25.7 and a 28.6, you're going to have to go back and really go and calculate this a little bit further. Like at that point, maybe you do 908 times 0.45 and get a closer answer for your numerator. But most of the time, you're going to be 100 away, or it'll be more obvious for you that all of the answers are kind of further apart from where they are. In the study guide, there was one particular problem like that, and you can kind of look at if you estimated high or low to get closer to the answer. So everybody see, scientific notation really will help you put things in simpler form for you to get the correct answer. And then make sure you don't forget significant figures and units. All right, so now try this problem. Same approach. Look for numbers that have simple dividing, simple multiplying, and then handle your exponents at the end. So the correct answer for this one is 3.38 gallons. How many of you were close to that? Somewhere in a 3 range. Hey, that was many more than before. All right, so let's just quickly look at it. You could approach this 2 different ways. And for this exact problem, it's sort of the same approach, but sometimes it's easiest to look for numbers that can be canceled out in a numerator and denominator before you start. So say this wasn't almost 1 and it was like 55. You might want to do this approach first just to narrow that down and make it a little bit easier. So if we do that, then that's 12.8 divided by 4. That's just 3.2, right? So we could take 3.2 and divide that by what is essentially just 1. And that's really close to the answer, right? Or you could have taken your 12.8 and still recognize that this is roughly 1 times 4 and divide that by 4, and you still get about the 3.2. How do you estimate that your answer should be a little bit higher? What are you looking at, the numerator or the denominator, to decide? The denominator, right? Because we didn't estimate anything in the 12.8. We didn't round anywhere. We did take this. This number should, in fact, be lower or higher? Lower, right? It should be a little bit less than this, which means that if my denominator number is smaller, then my answer should be a little bit larger. So you should be a little bit more than 3.2 gallons. Good? Okay. Number 3, this one has a few more steps, similar approach. Go ahead and try that. The exact answer for this one, oh, I'm wrong. I'm so sorry. I said it was similar. I forgot that I added this piece onto this and this here. There's a factor of 1,000 that I didn't explain just now. But anyway, it's 0.0330 gallons. Okay. So what I was saying is it looks similar to number 2 because it had all the same components essentially except for the 1,000. So that would have been multiplied by a factor of 10, then divided by 1,000 there. So essentially divide this answer we had by 100, and you can see that it's almost the same thing. You would never have to do that. I'm just pointing that out. Do you see it? Okay. So same approach. You could do the 125 divided by 4 before you start, or you could just go ahead and handle it. So I'm going to take my, I don't have much space to write here. I'm just going to erase this for now. I'm going to take 125, and I'm going to divide that by the denominator. So I have 1,000 times essentially 1, right, times 4. So that's about 4,000. And did I go too high or too low? It should be a little bit lower, right? So I'm just going to tell myself it should be a little bit lower. So what's easy to see? 4th grade math, what's easy to see? 12 and 4, right? 12.5 divided by 4. So I'm going to take 12.5 times 10 to the first, and I'm going to divide that by 4 times 10 to the third. Do you see how I put exponents in there to make sure I'm getting the right answer? So now I'm going to do 4 into 12.5, and I get roughly 3 times 10. 1 minus 3 is a negative 2. My answer is about 0.03, which is what it is, right? And we said that this would have been a little bit lower, therefore my answer would have been a little bit higher. And then this is for sig figs. So I just want to point out to you, this has 3 sig figs. This has unlimited, because a conversion factor is an unlimited significant figure. Unlimited sig figs. 4 sig figs, unlimited, unlimited, unlimited. There are exactly 4 quarts in 1 gallon. That does not have a significant figure to it. It's just unlimited. Does everybody understand that? So then my answer should have least number of sig figs is 3 when multiplying and dividing least sig figs. So my answer has 3. Just to point out, if there's a decimal in the number, you find the first non-zero number, that number, and everything after it is significant. So the 0 at the end is still significant. Any questions with these? All right, with the metric system, I threw these up here just because you should probably at this point not have to use King Henry died by drinking chocolate milk, but it's possible that you may still need to. So I'm just going to rewrite that for you, and we're going to really talk about it in terms of tens, multiples of tens. So we know that this is the biggest. This has 1,000, and then here we have 100, and then 10 base unit. And then this is 0.1, 0.01, 0.001. But really, it's better to think of this as, all right, this is small, so there are 1,000 of these in a base unit. There are 1,000 base units in 1 kilo, right? You have to have the scale in mind of what's big and what's small. This is big, these are small. So there's 1,000 millis in 1 base unit. You also need to know micro, nano, and pico. So the way that I remember that is it's alphabetical, M-N-O-P, micro, nano, pico. So if you take the milli here, let me rewrite this. So milli is 1,000, okay, milli. The micro comes after it, nano comes after that, and pico because they're alphabetical. This is 1 times 10 to the third, agreed? Milli is 1 times 10 to the third. Then micro is 1 times 10 to the 6th, nano is 1 times 10 to the 9th, pico is 1 times 10 to the 12th. It's an easy way to just memorize it. Micro, nano, pico, alphabetical order, and they go up by 3 every time. So a pico unit is one of the smallest units of measurement that we use, okay? Any questions with that? Because you will be expected to just know these. If I ask you to represent something in micrograms, and you're doing like a dimensional analysis problem and you come up with an answer in grams, I expect you to know that conversion on your own. I'm not going to offer that to you anymore. Any metric conversions in AP, they'll never be given to you because we expect you to have them memorized. Good? So the study guide, we'll just go page by page, and then you just stop me on any problems that you want some answers for. Please realize that you may think, I shouldn't ask this because I should know it, but probably half of the class is thinking the same thing. So ask me anything. You should ask anything. The only time I've ever even like hiccuped at somebody's question or answer was I asked for like a numerical answer once, and a student said the letter L. It was like a numerical answer, like how many grams are in a kilogram, which would be 1,000, and his answer was L. And I was just like, did you just say L? That is the only time I may ever mock you, is if it's something that horrible. But he just wasn't paying attention. So, any questions at all in the study guide? Let me show you how to do it. All right, page 1, 1 through 4. Anything there? Number 1 was definitely what I was just talking about. You have to just memorize these and understand them. So on my own paper, I didn't just guess. I wrote out all of the prefixes and then just kind of kept matching them back and forth to make sure I didn't mess it up. So if you see on my paper here, I wrote out all of the prefixes. When I take a test, I don't want to ever just assume that I guessed correctly as I was thinking about it. I like to write everything down. Anything there? Yep. 4. So when I first looked at this question, because I redid the study guide again this year, I have obviously done it before, I think what ended up happening the first time I looked at it, I skipped over what the first sentence said and just went straight to the data. Did anybody else do that? I just immediately, right? Like you're kind of in a rush, you want to get it done, especially on a timed test, and I just looked at all the data and I was like, sure, that looks accurate and precise, but accuracy is only if it matches what it's supposed to be. And it said in the sentence first, it's supposed to be a 1 gram mass. 1.2 is not 1 gram. So it's not accurate because it's not meeting the reference or the standard that it's supposed to be. So it is precise, though, because all of those masses are really close to each other. In fact, with that error analysis with the plus or minus 0.001, you'll get to the same exact answer for all of them. So they're not accurate, but they are precise. All right, page 2. 5, 6, 7. I know you want 7. Anybody want 5 or 6? Okay. Number 7 is, the approach of this is just automatically like, wow, this is a lot of stuff. So probably best scenario is to write down the information that you know. So when we did dimensional analysis in Honors Chem, and even if you didn't have me, one of the main things you should always do is write down knowns and what are conversion factors. A conversion factor is like something equals something else. Like 4 quarts equals 1 gallon. That's a conversion factor that I can use to get me to another piece of information. The one thing that probably threw you off a little bit in this problem is that it asked for the length of an oleic acid molecule. But length, when you look at a cube, and I think this even happened when we did the aluminum foil, some of you would call the height length. There's length and width and height, but when you look at a cube, it's kind of like up to you, really, right? Where you say length, width, and height are, depending on where you're looking at it. So I personally didn't like the word length. I knew what it meant by thickness. What did I change that word to, do you think? Height. Because we did the same thing with the aluminum foil lab. We determined the thickness of aluminum foil, but we looked at height. So here's what I wrote down to start. I said my known information is 3.25 times 10 to the negative 6 grams, and the density 0.895 grams. And watch, if you've not had me, I never slash something like this, because then you don't see it. You don't see that that's a denominator conversion factor, do you? So anytime I see a slash something, I always write it like this. Now that looks like a conversion factor, doesn't it? Because this is essentially just saying 1 milliliter equals 0.895 grams, and then I can use this in a dimensional analysis problem. So I do get information that the area, which is equal to length times width, is equal to 20.0 centimeters squared. So I wouldn't need, right? This doesn't even make sense to find length again. I'm really looking for the height. And volume comes from length times width times height. So essentially, the length and the width are given to me as 20.0, but I need to find h, the height. And if I can find volume, then I can find height. How can I find volume? What unit here can give me volume? Grams or milliliters? Milliliters. And I already taught you that 1 milliliter is equal to 1 centimeter cubed, correct? So I could get myself to a centimeter cubed, which is what volume essentially is. I realize that this is a little bit, I'm talking about units, but you could have just recognized that height is going to be involved in a volume measurement. All right, so now I'm going to take my known information. 3.25 times 10 to the negative 6 grams, and I'm going to use this conversion factor. Maybe this is all you got to at this point, and you were like, well, I know I can do this. Now what? If you see that your units ended in a volume unit, then you'll recognize, oh, I could use volume to solve for height. So now I'm going to do this math right here. So the easiest approach would be to try to make it look like something that you can easily handle. What is something you could easily handle? Like 4th grade math. What would you look to do? You going to do 3 divided by 0.9? No? What would you do? Sure. Thank you. There's a few approaches here. Someone give me one of them. What's easy to do? Round this to 1, you could. Yeah? That's a little bit far off, but you could. And I think our answers are kind of close to each other. No one has any other suggestion? Yeah? Scientific notation for sure. So what would you want in scientific notation? This, you want to turn to an 8? All right, I'm going to just show you what I would do. There's 2 ways I would do this. I would look at this and say this is 3/9, which is what? 1/3, which is what? 0.33. That can happen like that, right? Look for things that are easy. So 3/9 is easy to handle, 1/3, 0.33. Or you could do 32.5 times 10, and I moved it once this way, but I got to go back that way, so that's times 10 to the negative 1st. Not negative 1st, sorry, it's a 6 already. So negative 7. Do you agree? And then what do you think I want to put down here? 9, because that's almost 9, right? So 9 times 10 to the negative 1st. 9 into 32 is a little simpler to handle, isn't it? So what's 4 times 9?
36.
Okay, so if this is approximately 4, that would be for 36, but 9 times 3 is 27, right? So I have 36 and 27. Where does 32 fall? Right in the middle, doesn't it? 32 is 4 away from 36, and 32 is like 5 away from 27. Do you agree? So I'm somewhere right in the middle here, so my answer is probably around a 3.5. Recognizing again that I rounded slightly up for this one, okay? So let's go with, this is about a 3.5 times 10, and then negative 7 minus a negative 1 is a negative 6, right? 3.5 times 10 to the negative 6 milliliters. Now, I'm just going to pause here for a moment, and then we'll finish the problem. If you preferred, you could have done the 3 times 10 to the negative 6th, and then done the 9 times 10 to the negative 1st, and recognize that's 1/3, or 0.33 times 10 here to the negative 5th, and then we have to put this in proper scientific notation, 3.3 times 10 to the negative 6th. It's almost the same thing, right? Just 2 different approaches. So you got to get to something that's familiar to you. This is really familiar. Make everything happen in scientific notation. All right, so now I have milliliters, and this is 3.5 times 10 to the negative 6 centimeters cubed at this point. Do you agree? That's where your brain should click. If you didn't know how to do this problem to start, you just start with your known and your conversion factor. At this point, it should have made sense to you. this is a volume measurement. What can I do with volume to give me the height? I know the area, and then it should have just started to click. Volume equals length times width times height. So I'm going to take this number, 3.5 times 10 to the negative 6 centimeters cubed is equal to length times width, which was 20.0 centimeters squared, times height. So now I divide by 20 for my algebra. I divide by 20 for my algebra, and now I need to solve this. So take a minute. Everybody think about this. What makes sense? What's the easiest approach here to see? Maybe different for all of you. Everybody think about what would be the easiest way to handle that. We don't want to do 3.5 divided by 20 because our brains don't really want to see that. Just give me 1 second, I'll call on you. Let everybody think for a minute. Okay, go ahead. Divide what? 4 and 20. You could like round that to 40 and 20. So then your answer's somewhere around 2. That's okay if our answers are really far away. But if you look at like where they are right now on the multiple choice, you're going to end up a lot higher, right? You're going to end up near like a 20 range when you divide 40 by 2. Which would be okay, but I think we can get even a little bit closer. But that's a good start. Jillian? 35 divided by 20, which is still a little bit, like my brain doesn't want to even do that. Go ahead. No, my brain doesn't even want to do that one. But yes, if your brain likes to do that, Randy? Isn't 35 divided by 2 a little bit easier? I don't know why. It is for my head. Because I'm like, oh, I could just quickly do 2 into 35. Oh, 1, 2, 15, 7. Oh, it's about 17. Like, doing old school math is perfectly fine when it's down to really simple numbers. And I liked all of your approaches. Like, you would have gotten 20. 20 is really close to 17. You're okay with that, right? And doing like a 3.5 divided by 2 is fine. But my brain doesn't want to do 3.5 divided by 2. It wants to do 35 divided by 2. I don't know why. So I'm just showing you how I would do this problem to make it as fast as possible. All right, so now we have to handle, though, our exponents. So I just did, watch, I did 35 times 10, and this was a negative 6. If I moved my decimal here, it wants to go this way, right? My decimal wants to go this way. So if I move it here now, it's times 10 to the negative 7th. Do you agree? Dividing that by 2 times 10, and this is 20 to the first. So we just said that's about 17. Let me erase this. So if that's 17, then I'm going to subtract my exponents. Negative 7 minus 1 is going to give me the negative 8. And then I have to put this in proper scientific notation. So it's 1.7. A negative 8 would have gone this way, right? But now it's one more closer to the way it's supposed to go. So it's times 10 to the negative 7th. So now I'm going to go look at my multiple choice. And there is a 1.82, which is probably pretty close. The 1.45 I would sort of look at and just say, well, is there any place where I rounded way too much? So at this point, I don't think I rounded too much, right? It should have been a little bit less, which means it's probably, this could have been a little bit more at this point for this answer. So maybe the 3.5 is slightly off, but for the most part, my answer is really close to where it should be, so I would not have gone with the 1.45. Okay. All right, page 3. Number 9, I personally think is a typo. I forgot to mention that to you. It should not say how many significant figures. It should say how many decimal places, because when you subtract using sig fig rules, essentially, you need to use least number of what? Decimal places. And in this one, when you subtracted your answer, did you get 0.0816? And then when you use least decimals, you get 0.08 after rounding. Agreed? How many sig figs is 0.08? 1. So really the correct answer here is letter A. If it's 2, they're trying to make you recognize how many decimal places it should be. But they didn't word it that way. They worded it how many sig figs should there be. So there should be 2 decimal places, but then that in our answer, it's only 1 significant figure. All right. Anything else on that page? 11. Mike, did you need anything before that?
Well, she said 11, so can you talk about 10?
10 with the, so did you set it up?
Not really.
Okay, so this is just, and this is what you're kind of hopeful for on my test and on the AP exam, is just a basic dimensional analysis problem. So it reached a value of $1,000 per troy ounce. So when I hear per, I write it as a conversion factor with a numerator denominator. At that price, what was the cost of 1 gram of gold? So 1 gram is my known. That's what I'm starting with here. So I'm going to convert now what it gave me as a conversion factor to troy ounce. And then I'll convert here 1 troy ounce, because I wrote down my own conversion factor, is $1,000. So now we need to do the mental math there. So you're basically taking 1,000 and dividing it by 31. So can you do that math? If you don't, do 3 into 10 and then put it into scientific notation. I mean, you should see that this is about 30, and then you'll look at your answer and it says between $10 and $50. But even if your brain doesn't want to do 30 into 1,000, I'm sure you can do 3 into 10, and then this would just be 10 times 10 to the second. All right, let's take a look at number 11. It says a 20 ml sample of glycerol has a mass of 25.9 grams. What is the density of glycerol in ounces per quart? What is density? What's it equal to? Mass over volume, right? So basically it's saying find a mass over volume and convert it to this mass in ounces over this volume quarts. So this is just a conversion factor problem where you're taking your mass, 25.9 grams that it gave you, over 20.0 milliliters, mass over volume. It now wants you to convert this, it says, to ounces and this to quarts. So now this is just a simple conversion factor. We're going to do 28.4 grams is to 1.00 ounces. And I've already converted my numerator to what I want it to be. So I'm stopping with the numerator. When you need to convert the denominator, where should you put the unit? In the numerator or the denominator? It should go in the numerator because it's here. So milliliters is going to go up here. And I don't have a conversion for milliliters to liters, right? Because you should just know it. There are 1,000 milliliters in 1 liter. And then I have a conversion for 1 liter to 1.06 quarts. So now I double check, my units are canceled, and I'm left with my numerator in ounces and my denominator in quarts. And now I'm going to do my mental math. So this one may take a little bit more time. So I'm going to do 25.9 times 1 times 1,000, so that's 25900. All I did was say anything times 1,000 is move my decimal 3 to the right? So my decimal 3 to the right gives me this answer. Divide this by 20 times 28 times essentially 1, right? This one's a little tricky, and I'll mention it now, because if you take a look at your multiple choice, letter A and letter D are really close to each other, aren't they? They're only 5 away. So the first time I did this problem, I solved, and I wasn't at the exact number for either of these answers, and then I saw it, and I was like, well, I'll go back and just refine my answer a little bit more, and I got dead on to letter A. So let's talk about the first approach and then how you could go back and refine it. So what I did here is I took 28.4 and I multiplied it by 2. I just did old school math at this point. So I said 0.8, 16, 5, 68, and then I realized that I'm multiplying by 2, but I really wanted to multiply by 20. So I need to multiply this by a factor of 10, right? So I'm just going to jump that decimal place over. So that's 568. So I'm essentially dividing by 568. Do we all agree? But because I took that 1 and rounded it down, really this should be a bigger number. And if this is a bigger number, when I solve, my answer should be a little bit smaller than what I get. Do we all agree? So my answer should be, whatever answer I get, should be a little bit smaller. All right, don't call out. Everybody just look. What's 4th grade math approach? What's easy to do? Let everybody try. Go ahead. 25 divided by 5, I agree. But is that 5? It's not really 5, and it's a little bit closer to 6, and I already said this number should be a little bit higher anyway, right? But I'm going to go with the 25 divided by 5, I agree, because that's easy to see. So that was my first approach, was to just say 25.900 times 10 to the third divided by 5.68 times 10 to the second. So 5 into 25, but this is really like 26, right? This is going to give me an answer of about 5 if this is 25 into 25. But if I take this and make this a 6, because this number is like halfway between 5 and 6, right? So I'm going to do both answers. 6 into 25 is what? About 4. You could tell I was looking at you, Jake. It says about 4. And this is halfway in between here, so I bet you my answer is somewhere in between like 4.5-ish, but probably closer in this range, like somewhere here. Why do you think I'm saying that? Because this should be closer to 6. It's not going to be really close to 550. It was closer to the 600. Do you all agree with that? So that's why I'm saying my answer is more in this range than it is in this range. But had you just went with the 25 divided by 5, you would choose the wrong answer. That's why you don't want to just round really far away from the number. You want to recognize, like, this is a halfway number. This isn't really all the way. And you would have done that. You would have gone back to it after you saw letter D, and you would have actually ended up with the 50 here. You would have chose D incorrectly if you didn't make sure that you estimated this a little bit more. So this is probably more like a 4.3-ish, I'm going to say, times 10. 3 minus 2 gives me a 1. So my answer is about 43, what part was I at? Oh, ounces over quarts. Ounces over quarts. And that's what it exactly gives you. That one's tricky. And I talk about that in the YouTube video a little bit about how to go halfway between numbers. Like choose the high, choose the low, and then recognize that it's in between. Any questions on that one? All right, we're good with 17. I mean, number 12, not 17, number 12. What did you do, sorry, before you flip over? If you chose letter D, which is probably what some of you may have done accidentally, what didn't you do? Mike? You didn't round. A lot of times that will happen, you're working too quickly, you see that you want it to be 4 sig figs, you just chop it, and you forget to look at the number after. So make sure you're careful. All right, page 4. Anything on page 4? Yep.
It lists the temperature for problem 16. We have to know that the temperature, like how it affects.
Well, that's interesting.
Floating.
Like you're saying, if the temperature of water is not what it is that what you're suggesting?
Why is the temperature there?
I think it's just giving you the scenario. If they wanted you to ever mess around with temperature, they'd have to be like really specific and I think there is a question in the book where they talk about the temperature and how it could change it, but they would make sure that was emphasized. So no, I don't think that was really meant to be there as a deterrent. I think it was just giving you information. What's the density of water? 1 gram per mil, right? You need to know that. Okay, we're good on that page? So last page, number 5. Page 5, I mean. Anything there? So those separation techniques are in the chapter that I gave you. At the end, it talks about different separation techniques. So a mobile phase and a stationary phase, you might have read a little bit about it, but I can elaborate a bit more on that. Any type of chromatography is specifically meant to separate a mixture. So a mixture, if you're even using like coffee filter paper, you blot like a marker, a red marker or a purple marker or something like that, and the ink will travel up for one color and then the next color would travel again. So that just separates it by color. But in the industry, we use what's called liquid chromatography or gas chromatography. And in this particular example, when you use liquid chromatography, you have a column, literally looks like a metal bar, and inside here are a bunch of molecules kind of making like a Brillo pad. It's like packed, like a stationary phase, like a packed Brillo pad of other types of molecules in there. And then they send through a tube here with the mobile phase, which is liquid. It's just basically a mixture of, say, acetone, you know what that is, and water, or there's other chemicals that we put in there. And then it travels through and it comes out the other end. Now you put in here a sample. Your mixture gets injected with a little needle, and it's mixed with A and B and C. Well, it'll start off together, but as it interacts with what's inside here, it pulls apart all the different molecules in the mixture. And so say component B really likes what's in this stationary phase, it gets stuck like this and it holds onto it. All the while, the liquid is running through the mobile phase. So if something really likes the mobile phase, it's not going to get stuck and it's just going to travel through with the liquid. So say part C really likes the mobile phase, then it comes out first. So it's first if it likes, and I'm using the word likes loosely here, meaning it interacts with it through intermolecular forces. But if it really likes the stationary phase, it's going to come out last. Do we agree? Because it gets stuck in there, okay? So maybe it's C, A, B. They come out separately, and then you have a detector at the end to analyze them. This is primarily what most chemists use to analyze any samples, forensics and analytical and all different kinds of chemists. But this horrible diagram that I just drew for you is like a $300,000 piece of equipment that goes in the lab. And then there's lots of other techniques that are much easier to use, like filtration, distillation, and so forth. Good with everything else? What is number 20 checking besides the right answer? Sig figs, okay?